So on number 7, it says to find the Taylor series centered at the given value of a. So for the first one, we're doing 3. And then give the first 4 non-zero terms. Okay. So if we want the first 4 non-zero terms, how do we do that? Yeah, so we're going to find, well, first, since we have a Taylor series that's not centered at 0, we have to actually do the derivatives. And one thing to be careful of is sometimes they'll talk about find a 4th degree, which means you want to have x to the 4th. Sometimes they'll say we want 4 terms, which is you just count the terms and have 4 of them. Okay, so, and that might be something you write down on your notes somewhere. There is a difference between saying 4 terms and 4th degree. 4th degree means I have to have x to the 4th. 4 terms means I just count the different pieces and I have at least 4 of them. Okay, so this one just says 4 terms. So we're going to do the function itself is e to the 2x. The first derivative is 2e to the 2x. The second derivative, 4e to the 2x. Bye, Logan. Good luck with track.
Yes. How's it going to be?
It's not going to be AP style. It's going to be similar to how these worksheets have been. Yeah. Nancy, don't do this to me. 2, 4, 2 cubed. I'm going to say 8. Yes, 8e to the 2x. Okay. And even though this is only the third derivative, this should be enough information to give us 4 terms. Okay. It also wants the general term, so we're also going to find the nth term. Okay. So the first, oh, actually I have to evaluate these, right? So f of 3, f prime of 3, bye, Leon, f double prime of 3, and f triple prime of 3. Yep. And then 2e to the 6th, 4e to the 6th, 8e to the 6th. So we have e to the 6th, and then x minus 3, plus
4e to the 6th, x minus 3 squared, over 2 factorial, plus 8e to the 6th, x minus 3, 2 thirds, over 3 factorial.
so that's the first 4 terms, plus dot dot dot. Wait, 2 to the n, e to the 6, to the n, and then we make sure plus dot 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 to show that that series would go on forever. And that was just the nth term. Okay. I think the next one is worth doing together because it's a little bit weird. It's got a weird part in it. Okay, so we have f of x is 1 over x. F prime of x, I'm going to go ahead and say that this is just x to the negative 1. Okay, so f prime of x would be negative x to the negative 2. F double prime of x to the negative 3. And then f triple prime of x okay. So f of 1 would be 1 over 1, which is 1. F prime of 1 would be negative 1 divided by 1 squared, which is negative 1. F double prime would be 2 divided by 1 to the third. Negative 6 divided by 1 to the fourth. Okay. All right, so first term is 1, okay, and then minus 1 times, okay, and then plus 2 times x minus 1 to the second over 2, okay, negative 6, x minus 1 to the 3 over, okay, this nth term is a little bit hard to find. Do you guys see what's happening with the coefficient and the factorials? Yeah, they're crossing out, they're the same. 2 is the same as 2 factorial. 6 is the same as 3 factorial, okay? Oh, so this is really negative 1 to the nth, because we're alternating our signs, right? And we're starting with the 0 term. And this would be n factorial times x minus 1 to the n over n factorial. And when you have these problems that have a fraction like that, that's how the exponents work. They always make those factorials, which is really interesting. So we can say like the 2's cancel out and the 6 and the 3 cancel and the factorials cancel out. So a simplified version of this would just be 1 minus x minus 1 plus x minus 1 squared minus x minus 1 to the third. So we could say our nth term, all the terms really are pretty simple. And don't forget that plus dot 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 that I forgot at first. Okay. It's not a dead animal, but it should be.
You can replace the...
Yeah, I took down the giraffe. We could do that. But then all the calculus ones are over there and there'd be like one random one.
We're learning, remember?
Yes.
We're growing.
Yes, we're growing in all directions,
Exactly.
even towards the pre-calc side, the dead animal wall.
Yes.
Okay. I think you guys will be comfortable with these for a little while. I think most of these are going to be okay.
Is it going to ask us in the packet to start at a degree? Or is
That says terms. We could do number 17.
Have we done number 13?
Oh, we would need to do number 13. I mean, we could do number 13 and then do number 17. Okay, let's do number 13 and then do number 17. Okay. So number 13 is asking about the Maclaurin series, right? So what's the Maclaurin series for sine?
X minus x third, 3 factorial, plus x to the fifth over 5 factorial, dot dot dot. Oh, okay, x 2n to the 2n plus 1 over 2n plus 1 factorial.
Perfect. Okay, so to do number 13, what should we do?
Wait, shouldn't we do the minus 7?
We can. Yeah, any place I see an x, I'm going to do an x squared. So I'm going to have x squared minus x squared to the third plus x squared to the fifth. We can do the next one if we want. Oh yeah, because it said 4 terms. Shame on me. Well, we fixed it. Here we go. I was like, why is Emily being extra? But I was supporting you. I was supporting you in it. I was ready. But you weren't being extra. You were doing what the instructions said. Okay, so what we have, if we simplify it, is x squared minus x to the 6th over 3 factorial. X to the 10th, good. Apparently I had given you guys this problem before because on my answer key I say I'm not doing this problem again and I just write out the answer. Oh, that's funny. That's what happens when I make too many answer keys in a row. I get frustrated. This teacher just doesn't stop assigning work. X to the 4n plus 2. Okay. So now that we have 13 done, we can go to number 6. Was it 16? 17. Yeah, we had looked at 17 because the wording of 17 was like different than the other ones. But then we realized to do 17 we had to go back. Okay.
How did we end up with 4n plus 2 again?
We took this x squared, the 2 right here, and we distributed it.
Okay, that's what I thought.
Yeah. Are you working on that puzzle? Thomas, work on this page. Oh, you're tracking with us?
Yeah.
You're multitasking with a puzzle.
Yeah, make me think really.
Yeah, that's like a whole different level of nerd, you know? Put down that puzzle and participate, you know? Once at my old school, I had to confiscate a kid's Rubik's Cube because he would not stop messing with it.
Yes.
So I was like, I can't believe I'm doing this, but put that Rubik's Cube in cell phone prison. All right, so we are going to do the integral from 0 to 1 of sine x squared dx, but we're going to do it by using as many terms as we need to get 3 decimal places of accuracy. Cool.
Some zeros.
Tack on some zeros and call it good? No. So let's go ahead and see what this actually is so that we can see how many terms we're going to need. Yeah, I was waiting. I didn't want to, because sometimes students wait for me to be the calculator. So I was making sure you guys had time to type it in.
I thought you were looking at it and just waiting.
No, I was looking at it and waiting for you guys to tell me.
Yes, press enter.
And
If we
3,
don't,
1,
or
0,
when
2,
we're typing
6.
the ones with the factorials in, you don't have to put the numerator in parentheses, and it won't mess up our answer. It's just the factorial.
if you have like a something factorial on the bottom, that would need to be in parentheses, or else you could just plug it in as a fraction
Yeah.
to make sure that you're doing the factorial only goes to that number and not to like the whole answer you have so far. Yeah. Okay, so we have
No. That is wrong. Let's get a different value.
I'm in degrees. Okay. So we have to get as many terms as is required to make our answer become 0.310. That's how we know how far to go. Does that make sense? Okay. So I evaluated this. I got 0.310. Are you guys ready?
I have a question.
Yeah.
I was looking and it's 16. There's a different than 13? Or...
It's different because it's, so this is a great question. So number 13 said sine of x squared. Sine squared x really means sine x squared. And so that's why I gave you a hint for that, because you can't do it the way it looks right now. You have to use the power reducing formula to change the problem, and then you can do it. Yes. Yeah, so they're two different problems. And that's exactly why we say sine squared, because if you said sine x squared without the parentheses, then you'd actually be saying the x is squared, not the whole thing. So that's why we write it like that, because we're lazy. We don't want to put the parentheses. Okay, it's fine. Okay, so for this one, we want to see how many terms we need to get 0.310 from our answers. So we are going to be integrating x squared minus x to the 6th over 3 factorial plus x to the 10th over 5 factorial minus x to the 14th over 7 factorial, and hopefully at that point we'll be done. But I'm going to leave a ... there just in case we need to keep finding more terms. Okay, so when we integrate, what's our first term? 1/3 x to the 3rd, okay, minus
7 times 6.
yeah, x to the 7th. No, 11th, right?
I mean 11, sorry.
It's okay, so many things are happening with this problem. The 11th, okay. Minus 7 factorial x to the 15th. Okay, so I'm gonna put plus ... for now, so that, and I'm gonna leave some space so we can find some more if we want. But we're evaluating this from 0 to 1, right? What's gonna happen when we plug in 0? We're gonna get nothing. Okay. So we can basically think about plugging in 1, and we can just start plugging in terms and see what we get and add more and more terms until we get the right answer. Okay, because we want to have 3 decimal places of accuracy. We're going to see how many terms it takes to do that. So I'm going to go ahead and type in 1/3 times 1 to the 3rd in my calculator, because it says we can use our calculator.
Why would we just plug in the whole integral?
Because we don't know how many it's going to take, Tanner. All right, so that's 1/3. And then minus, I'm going to need the next term because I'm not there yet. Minus you hit the math button and go to PRB and then go down to 4. Oh, we're a little bit closer. Actually, that's kind of it. Well, not if you round. We'll actually go a little bit further. I mean, that's rounded, yeah. Plus I don't know why I'm typing in the 1s. Times 1 to the 11th, because it's going to change it. Did I type that right? Ta-da! There we go. So we only needed 3 terms to make that happen.
So when we see questions like this,
Mhm.
we're supposed to just type in the original integral, and then we have to see.
We After the quiz, we're going to learn about how to compare the actual answer to the approximate answer. And it's called talking about the amount of error that you have. The error would be like how far off of the real. With the what?
Like the standard error or no?
Kind of, well, it's not really statistics, but it's kind of the same idea of like the actual decimal compared to what you get and how far off you are. I guess it'd be kind of similar to the idea of confidence intervals a little bit. Of like, well, we're going to find an interval and the answer has to be in that interval, basically. So we're done with that one. Is there anything else in here that's making you uncomfortable at all? If you look through.
So you go for it.
Okay.
What does series expansion mean?
Series expansion is what we've been doing. This is a series expansion.
Okay.
Okay. So the plan is to work on this assignment, to work on the Taylor and Maclaurin assignment for the period, and then at the end of the period we'll evaluate where we're at and see like how many we think we could finish without like me killing you, basically.
Hate these ones.
You hate them? The confidence interval,
That we did yesterday?
or not confidence interval, the interval of convergence. You hate that stuff.
Hate it.
It's a little tedious. It's not the most fun.
Yeah.
So we're not working on.
You're working on both. You're kind of going back and forth, getting a good mixture of both of them. We've done a little bit more in the first packet, so I'd say maybe work on the other one for now. But you've kind of noticed they're very similar. Have you noticed that? There's a lot of, like, even though we've switched over to this packet, we're still like, oh, more Taylor and Maclaurin. So.